Okay, so now we're going to talk about the addition rule. Now, before we get into the actual addition rule, we need to actually look at one definition, and that's the definition of uh, mutually exclusive events or disjoint events. All right. Now, event A and B are disjoint or mutually exclusive if they cannot occur at the same time. Basically, this means that there is no overlap for the events. There's no intersection for the two sets because remember, events are subsets of our sample space. Here's an example. We're going to look at these two events and we're going to determine whether or not these events are disjoint or mutually exclusive. Right, so event A would be randomly selecting someone treated with the cholesterol reducing drug Lipitor. I'm going to call this event A. And the second one, randomly selecting someone in a control group given no medication. I'm going to call this one event B. And the question is, are event A and B mutually exclusive? So what you have to think about when you need to answer that question is, can those two things, event A and event B, happen at the same time? So if we select a single person, can that person be someone who is both being treated with the cholesterol reducing drug Lipitor and also at the same time in a control group who's being given no medication? Well, obviously that's impossible for those two events to happen at the same time because either you're being given medication or you're not. You can't be doing both at the same time. So in this case, for number 10, this is actually 10 from your exercise set. These set of events are disjoint, which means the same thing as mutually exclusive. So these are disjoint events, mutually exclusive events. So disjoint and mutual exclusivity mean the same thing. All right, let's take a look at another example. So here's another one. This is these are the two events. The first event is randomly selecting a college student. So that's event A. We're going to select somebody and that person is going to be a college student. Event B is randomly selecting someone who is homeless. So that's event B. Or actually, not a college student, but a college graduate. So event A is randomly selecting a college graduate, and event B is randomly selecting someone who is homeless. Well, what you have to do is say if you selected a single person, could that person be both a college graduate and also be homeless at the same time? Well, even though we'd like to think the contrary, this is actually something that can, these are two events that can happen at the same time. There are college graduates who are homeless. So these two events are not mutually exclusive. So they're not disjoint. Not disjoint. And not disjoint means the same thing as not mutually exclusive. So that the word disjoint and the phrase mutual exclusive are synonyms for each other. All right, so that's the discussion that we have to talk about. What we had to talk about as far as disjoint and mutual exclusivity. Now let's talk about the addition rule. All right. Now this is the intuitive addition rule actually, and intuitively what the addition rule says is to find the probability of either A happening or B happening, we need to find the sum of the number of ways that event A can occur and the number of ways that event B can occur. But when we're finding that sum, we have to add in such a way that every outcome is only counted once because there is such thing as double counting. When I show you the example, you'll see what I'm talking about. So the probability of A or B is equal to the sum of those two things divided by the total number of outcomes in the sample space. All right, so here's what it looks like formally. Formally, it says that the probability of A or B, so the probability of A or B is equal to the probability of A, so you first have to know the probability of the first event, plus the probability of B, so you have to know the probability of the second event also, minus the probability of A or B both happening at the same time. Minus the probability of A or B happening at the same time. Now, if your two events are mutually exclusive, if your two events are mutually exclusive, then it turns out that the probability of A or B would be equal to, now this is only for mutual exclusivity. So if your two events are mutually exclusive, then the probability of A or B is just the probability of A plus the probability of B. And you don't have to subtract the probability of both happening at the same time, because in fact, they cannot happen at the same time. So mutual exclusivity reduces this formula to just the sum of the probability of A and the probability of B. So it's very good to know whether your two events are mutually exclusive or not. So let's take a look at an example here. So this is an example from your exercise set, actually. This is example 30 from the exercise set. And it says in exercise 27 through 32, refer to the following table summarizing results from a study of people who refused to answer survey questions based on data from I Hear You Knocking But You Can't Come In by Fitzgerald and Fuller. So this is basically a sociological uh, s- um, data set. This data is collected by calling people and asking them survey questions. Across the top, we have the age demographic. So this column represents 18 to 21-year-olds. This column represents 22 to 29-year-olds. This column represents 30 to 39-year-olds, and so forth. So basically, across the top, we have different ages. Now, we have two rows here actually. One row is for people who actually responded to the survey question. That's this top row here. And the other row is for people who refuse to respond to the survey question. That's the row underneath this one I just circled. So basically, if you look at the intersection of a row and a column, for instance, if you look at the intersection of this row and this column, these 255 people are between the ages of 22 and 29, and they actually responded to the survey question. So that's how you read these two-way tables. The intersection of a row and a column, if you look at the heading of the column and the heading of the row, that intersection tells you what the demographic for the people you're looking at is going to be. Right, so let's take a look at this first example here. The first example says, what is the probability that the selected person refused to respond, or, you see the word or there, or is over age 59. So let's take a look. We have the or here, and we have two events. The probability that the person refused and the probability that the person is over 59 years of age. So let's let A be the event that the person refuses, and let's let B equal the event that the person is over 59 years of age. Well, if you're over 59 years of age, what that means is if you're over 59, that means you are 60 and over. And that turns out to be the last column of our chart. And the people who refuse to respond are the bottom row of our chart. So what we need to do is we need to look at the probability of A or B. And you see it's all set up here. We have event A, person refused, or, the word or, B, the person is over 59 years of age. So what we need is we need the probability of A. That's the probability that somebody refuses. And we're going to add that to the probability of B. And the probability of B is the probability of selecting somebody over age 59. And what we're going to have to do is subtract the probability of someone who refused and is also over 59. So the people who refuse and are over 59 are these 49 people right here. These 49 people, not only are they 60 and over, but they also refuse to answer the survey question. So let's look at the probability of A. The probability of A is the probability that somebody refuse to answer the survey question. So how many people in this table refuse to answer the survey question? Well, it's these 11, and these 20, and these 33, and these 16, and these 27, and also these 49. So we get a total of 156 people who refuse to respond. So I'm going to make another column over here for the total. And the total of people who actually responded is one, or refused to respond. Sorry, the total of people who refused to respond is 156. All right, now let's look at the people who are over 59 years of age. So now we're going to look at event B. Well, how many of these people are over 59 years of age? Well, it's this column right here. So I have these 202 people plus these 49 people. So it turns out that this sum is equal to 251. So this column totals to 251. Now let's go ahead and create our probabilities, all right? Well, in order to create the probability, we need to know how many people there are in total in this table. So in order to find that out, we add up all these numbers. So we have all the numbers have to be added. In that case, we're going to get the grand total. We're going to get a grand total here, let's see, of 1,205 people. So there were 1,205 people total. So what I've done is I've taken all the numbers in this table, except for the ages, of course. I've taken all of uh, the people who responded and the people who refused to respond, and I've added them all up. And the grand total was 1,205 people. So it turns out that the probability of A, this number here, the probability of A is the total number of people who refused to answer the survey question, which is 156. 156 divided by the total number of people, which is 1,205, plus the probability of B is going to be, well, there are 251 people who are over 59 years of age. So that's 251 out of a grand total of 1,205. And then we're going to subtract from that the probability of somebody being both over 59 and also refusing. Well, you remember these 49 people? I don't know if you realize this, but we counted those 49 people amongst the 156, but we also counted those 49 people amongst the 251. So we actually counted those 49 people twice. And in order to correct for that, because we can only count each individual person once. In order to correct for the fact that we counted these people amongst the people who refused to respond and also amongst the people who are 60 and over, we have to subtract those 49 people because we've actually counted the 49 people twice. We're subtracting off one of those countings. 1205, and then we get a total of 358, and that is going to be divided by the 1,205 people. So it turns out that our probability that we're looking for, the probability of A or B, the probability that somebody either refused or was over the age of 59, turns out to be, let's do that division, 0.297 as a decimal, or as a percentage, 29.7%. So there's a 29.7% chance that we get either somebody who refused to answer the survey question or was over the age of 59. Okay, so let's go ahead and okay, the next objective is the rule for complements. Now, here's the definition, or actually we had the definition of a complement, but here's a rule that's going to allow us to calculate the complement of an event if we already know the probability of that event, okay? So the probability of A plus the probability of A's complement has to equal 1 because A and A's complement make up the entire sample space. Because the definition of a complement is all the events that are not in event A. So if you combine all the events in event A, or all the outcomes in event A, with all the outcomes that are not in event A, you get the entire sample space. And when you add up the probability of all the outcomes in the sample space, you should get 1. The sum of all the probabilities should equal 1. And if you solve this equation for the probability of a complement, then you get that the probability of a complement is 1 minus the probability of an event. And if you solve it for the probability of the event, you get that the probability of the event is 1 minus the probability of the complement. So let's take a look at this example. When the author observed a sobriety checkpoint conducted by the Dutchess County Sheriff Department, he saw that 676 drivers were screened and 6 were arrested for driving while intoxicated. Based on those results, we can estimate that the probability of intoxication is equal to 0.00888. This is by the relative frequency method. If you take 6 and divide it by 676, you should get 0.00888, where I denotes the event of screening a driver and getting somebody who is intoxicated. All right. So now they want to know what's the probability of being not intoxicated. What would be the probability if one of the drivers were selected from this night that the driver was not intoxicated? Well, by the rule we have above, that would be 1 minus the probability of getting somebody who is intoxicated. And we have that probability. That's 1 minus 0.00888. And 1 minus 0.00888. Let's see the calculation. 1 minus 0.00888 is equal to 0.99112. So that's 0.99112.